Good evening. We're going to be talking about FreeFall for the next couple weeks. We're going to keep it easy to start with, and we're just going to be going straight up and straight down. And that way, all we'll be talking about is gravity. And what we look at, would you volunteer to catch a baseball dropped a few feet above you? Okay? Or would you volunteer to drop if you got one from the Sears Tower? Well, the Sears Tower is about 100 stories high. It's about 10 feet per story, so that would be 1,000 feet. Would you try to catch a baseball after that one? I don't know. If you can, the Rangers might want you. The good thing about freefall is that we're under the influence of gravitational force only. Okay? And falling objects accelerate at a constant rate. This is one of the things Galileo got in trouble with. Because before Galileo, people thought that if something had twice the weight, it would fall twice as fast. That goes back to Aristotle, so the old Greek thinking was still around. And Galileo had done the math, and he understood that everything should fall at the same rate, this 9.8 meters per second squared. So it didn't matter if you were an elephant or matter if you were a mouse. Okay? But Galileo was a little bit wrong because he didn't take into account this idea of air resistance. Okay? Anytime you're free falling, the factors that affect your air resistance are your mass, your surface area, and your shape. So if you have a 1 kilogram ball of metal that's like that and a 1 kilogram sheet of metal, which one's going to fall at a faster rate? Okay? Well, out in the air, the ball will fall a little faster. This has too much surface area. Okay? There's an old video of like Buzz Aldrin on the moon in a vacuum, where there's no air resistance, and he drops a hammer and a feather and they drop at the same rate. It's actually pretty cool. Then there's this idea of terminal velocity. Terminal velocity is the point at which you do not accelerate anymore. Okay? So that's the highest speed you reach. If you go skydiving, it's about 120 miles per hour. Okay? At that point, okay, the force of gravity down equals the air resistance up. So your net force is 0. You have no acceleration. No acceleration, no net force. So how does a ball move when it's thrown straight up? If you throw a ball straight up in the air, a volleyball or a baseball or whatever, you kind of have to think, what happens to the acceleration on the way up? What happens to the velocity? Okay? Well, the velocity, the instant the ball leaves your hand, what is the ball going to start to do? It's going to slow down. Okay? What about the ball's acceleration? Think of it this way. Is the acceleration due to gravity ever change? Not as long as you're close to the surface of the good planet Earth. So going up, the ball is the minus 9.8 meters per second squared. What happens when you get to the top? What happens to the velocity? What happens to the acceleration? Well, what does the velocity do if you throw a baseball, right, and it gets to the top? There's that instant of hesitation where the ball's velocity is going to be 0. But what's its acceleration? It's not going to change. It's still going to be your minus 9.8 meters per second squared. The acceleration due to gravity doesn't change. What happens to the ball's acceleration on the way down? What do you think the answer is there, folks? And to the velocity? Well, we speed up going in a negative direction. Okay? What would a velocity versus time graph of a ball thrown straight up in the air look like? Well, even before that, what if you had a distance graph? Okay? If you threw a ball up in the air, you'd get something like that. Okay? Up at the top here, you would have your velocity equal to 0. Okay? So if you did a velocity graph, what would that look like? Okay, you know that's the fastest when it's leaving your hand, and you know it's 0 right here. So it's going to go down like this till it reaches 0, and then it's going to come back down, increasing in a negative direction. Now, if you're really smart then, if you make an acceleration graph, What does the acceleration graph look like? Well, the slope of velocity gives you acceleration. That's an A, sorry folks. Is the slope positive or negative? Well, it's negative. Is that slope constant or changing? Well, it's constant. So your acceleration graph would look just like that. Calculating speed, just use kinematics. We'll keep it simple. We'll take our initial velocity and make that equal to 0. So we end up with this velocity final is acceleration times time. Okay, it's pretty straightforward. If we jump off a cliff at the lake that's, and fall for 2 seconds, well, t is 2, a is 9.8. How fast are you going to be going? You just multiply those two together. So if an object is dropped from at rest from the top of a cliff, how fast will it be going after 1 second? After 2 seconds? After 10 seconds. Okay, what are your givens there? Well, the acceleration due to gravity is always 9.8. Your A is 9.8 meters per second squared. And these are your times. Okay? So your answer is 9.8 meters per second minus 19.6 and minus 98. Those would be straight plug and chug. You just got to keep track of what's what. Calculating distance, we can do the same thing. If we take our initial velocity as 0, that term will go away. So our distance in free fall, okay, theoretically it's not going to matter, is 1/2 acceleration times time squared. And again, our acceleration is still 9.8 meters per second squared. Okay? So how far down will you find an object? Dropped off a cliff that falls for 5 seconds? Okay. Well, what are you given? We're given the acceleration due to gravity at 9.8 meters per second squared, and we're given that it falls for 5 seconds. Okay, and what comes down to, if you go back, plug into the equation, 1/2 at squared, you come up with a minus 122.5 meters. Again, what's that negative showing you? Can you have a negative distance, a negative displacement? Sure you can. It's just telling you which way you're going. The demon drop at Cedar Point Amusement Park, that's kind of like something they used to have at Six Flags, okay? And they would strap you in and you'd fall for just 1.5 seconds. That's all you would do. You'd wait 30 minutes for a 1.5 second ride. What's the velocity after a second? After 1.5 seconds, what was your velocity? Do you remember? Acceleration times time. How far does it fall? How far? There's your distance. 1/2 at squared. So you calculate your velocity there. 1.5 seconds, 9.8 meters per second squared. And how far? 1/2 at squared. Okay? Hopefully that helped you out a little bit. Hopefully this puppy is working. Thank you.